Hello and welcome again. This is the second part of the video where we are trying to efficiently formulate the LQ optimal control problem to a standard QP problem. The LQ optimal control problem has this structure, and the standard QP problem has this structure. Now, in the part 1 of this video, we could efficiently convert the LQ optimal control problem's objective function into the objective function of the standard QP problem. In other words, in the previous video, we calculated H matrix and C vector. Now, in this video, which is the part 2, we will try to convert the constraints of the LQ optimal control problem to the constraints of the standard QP problem. We will try to convert the constraints of the LQ optimal control problem to the constraints of the standard QP problem. We will first start with the equality constraints. Here you can see that in the original LQ optimal control problem, there are 3 equality constraints, and all of them are linear. These 3 linear equality constraints should be converted to this structure, or this form. So, our goal is to find the matrix A and the vector B. Let's make those vectors and matrices. Here, I will be filling up all of the elements of the matrix AE. Of course, the matrix AE is being multiplied with Z, as you can see it here. And we know that our Z vector contains U, X, E, and Y. And in this box, we will be filling up the elements of B. Since there are 3 linear equality constraints, let us also divide this matrix AE into 3 rows. Each of the rows corresponding to each of the linear equality constraints. From the first linear equality constraint, I will write AE part of AE, but from the first equality constraint. For the second row, I will write AE, but from the second equality constraint, which is this one, and similarly we will have AE3, which shows that it is from this third equality constraint. Now, since each element of AE will be multiplied to each of the unknowns in the vector Z, we will have 4 different columns, so for the first component of the unknown vector Z, which is U, I will write it as for the first element, which is U. For the second element, which is X, we will have another column. It still is from the first equality constraint, but it is for X. And so on for the 2 remaining components of the unknown vector Z. Let's go to the second equality constraint. This second equality constraint will also be multiplied, or should also be considered for each of the elements here, so we will go on filling up the column part. The first one is for U, so here we will write U. The second one is for X, so we will write X. And similarly, when we consider the third equality constraint and all of these unknown variables inside Z, we will have the following elements. Now our goal is to find each of the sub-matrix X of this matrix AE. Since we have 3 equality constraint, let's divide B also in 3 parts from the first equality constraint, from the second equality constraint, and finally from the third or the last equality constraint. For this case, now let's fill up this matrix A with all of these elements, and let's also fill up this vector BE for all of these elements. We will take each of the equality constraint turn by turn. Let's first start with the first equality constraint. This equation can be written as follows. And when we replace k plus 1 with k, then we'll get the following equation. Now this is the constraint in the process, and this constraint has to be fulfilled for its discrete time step starting from k equals to 1 to k equals to n, or in other words, the constraint has to be fulfilled for each discrete time step starting from k equals to 1. This constraint has to be satisfied throughout the prediction horizon starting from k equals to 1 state to k equals to n time steps. So for k equals to 1 we have this expression, and here you can see that x0 is the initial value of the states of the process. And we all know that the initial value of the state of the process is the number of states of the process, and we know that the number of states at k equals to 1 at the initial time step is a known quantity. So a into x0 is a known quantity. All of the known quantities should be taken to the right-hand side of the equation. That's why we have taken a into x0 to the right-hand side. So the key point here is all of the unknown variables should be towards the left-hand side of this equality constraint, and anything related to the unknown should be taken to the right-hand side. And that is valid not only for first equality constraint, but for all of the constraints in the process. All right, now for k equals to 2, for the second time step we have this expression, but if our process has multiple states and x number of them, then this 0, which is on the right-hand side, will have an x number of zeros. Now we have written the state equations for all the prediction horizon length. Now these equations should be arranged in a matrix form. Let us do that. And remember, since these equations are for the whole prediction horizon length, our unknown variables we should also consider for the whole prediction horizon length. I will first start with defining the unknown variables, or the z-vector, and we know z-vector contains u, but I want to write also u from the whole prediction horizon. U starts from u0, u1, and all the way it goes to u of n-1. First element of z, and then we had x for the states. X starts from 1, 2, and it goes all the way to x of n. And then we had two more. First we had error. Error also starts from 1 to whole prediction horizon, n number of them, and finally the y. This is my z-vector for the whole prediction horizon. And here I will be making the part of the AE matrix, and of course the AE matrix will be multiplied with the z, and out from here we will get the BE part, or the first part of the BE. Now to fill up this matrix, we have to look into the equations that we just wrote for the whole prediction horizon. Let's start one by one. Start from this first equation. In this first equation, we see the coefficients of all of the variables that are here. What is the coefficient associated with u0? We know that it is minus b, so we can write minus b here. We should still look at the same first equation and go on writing the coefficients for each of these variables. u1, there is no term u1 in the first equation. That means the coefficient for u1 will be 0. Then we would have gone to u2. In the first equation there is no u2, so the coefficient will again be 0. We proceed further unless we reach u of n-1. For u of n-1, we also don't have anything here, still it will be 0. That was for the u part. We should continue going downwards, then let us look at the x part. First x1, still in the first equation. The coefficient of x1 is here, 1, but since it could be multiple states, more than one state, so instead of writing 1 we write I. There is no term for x2. That means the coefficient of x2 when we see this first equation is 0. We write 0 here. Similarly, there is no x3, x4, x5, all the way to xn in this first equation, so all of them will be zeros. That was for x part. Now we should do the same thing for the e part, and it's easy to look for the e part, as you can see from e1 to e of n in the first equation. There is no e at all, so all of them will be 0. e1 is 0, e2 is 0, e3 is 0, en is 0. That was for e part. Now finally we have the y part from y1 to yn. There is no y term here at all in the first equation, so it will also be 0. y1 is 0, y2 is 0, y3 is 0, y of n is also 0. Okay, we have now finished looking into the first equation, or equation, at the first time step. Let's now look at the equation for the second time step. K equals to 2. That means we have to look here. The procedure is the same. Start with u0. What is the coefficient associated with u0 in this second equation? There is no u0 at all here, so it is 0. What is the coefficient that is associated with u1? It is minus b. So here will be minus b. u2, there is no term u2, u3, all the way to un-1. Not present in these equations, so they will all be zeros. We have finished the u part. Let's do the x part. 10(1). What is the coefficient of x1 in the second equation? It is minus a, so this is minus a, x2. What is the coefficient of x2 in the second equation? It's 1 here, but since it can have many states, let's write I instead of 1. There are no coefficients from x3 to xn in this equation, so all of them are zeros. Let's see the e part. No e part here, and similarly for the y there is no y at all here. No y, so all of them zeros. Now we have finished the second equation also. Let's for simplicity do one more, and that is number 3. Let's start from u0, no u0 here, so it is 0. u1, no u1 here, also 0. Then U2 we have U2, and the coefficient is minus b. Here comes minus b. The remaining U3 to U of n-1 is not here, so they are all zeros. In the same manner, let's fill up x, no x1 here, so it's 0. For x2 we have x2 here, and it is minus a as the coefficient. Then we would have x3, so coefficient of x3 is I. There is no x4 to x of n, they are zeros. No e term, no y term, all of them zeros. And similarly, if we go on filling for k equals to 4, k equals to 5, k equals to 6, and so on all the way to k equals to n, we will get the following matrix. How about filling the known values or known quantities if we look into the first equation? Back again towards the right-hand side, we have a of x0, and that was for the first one. That is known, so we fill it up here. If you look at the second equation, we had 0, but an x number of them, so then we have 0. For the third, also we had 0, and so on for all of the n number of equations. Now we have finished making the first linear equality constraint into the standard form. This first part, which you can see it here, it looks like we don't need such a big area for the matrix, we can simply write it up to here. This part is AE for the first equation, and that was for you. This is from the first equation. With respect to x, and this is obviously from the first equation because now we are only seeing the equation, but that was for the error equation or error part, and this one is the output y part. So now we have some components of the AE matrix which are here. Now let's look at AE1U. AE1U is a nice structured matrix, which has minus b on its diagonal and the remaining elements are zeros. And this has a special way of writing by using the Kronecker product, and that is Kronecker product of an identity matrix of size n, where n is prediction horizon, NV. And similarly, the AE1X matrix is this one. Let's write it down. We have also talked about the special matrix that you can see it here. As you can see, the diagonal elements are all identity matrices, and this A is skewed with the position of -1. We can break this into two parts. Let's first consider the diagonal I elements, and that can be simply written as in dot of nx. Why we have to multiply with n? We have to see the whole prediction horizon, and we have multiple states nx. So total over the whole horizon for multiple states will be n dot of nx. Only this part would give you the I on the middle of your diagonal matrix. Here you can see it. But then we also have it with the negative sign. Then we can subtract that matrix with the shifted -a matrix or -a, which is shifted by position -1. And in MATLAB, this part we can write it as follows. Similarly, the AE1E and AE1Y matrices are all zeros, as you can see it here, and we can write them as follows. How many number of rows does this zeros for the AE has? Of course, this was for each of the state equation, but for the whole prediction horizon. So it should have n number multiplied with nx number of rows. And how many number of columns it should have? We can see it very clearly here. All of this will be multiplied with the E term, which is here. And the number of rows in the E term is n multiplied with ny of it. Thus it will have n dot of ny number of columns. And finally, we also have for the y part, which is also 0. How many number of rows? The same, n dot of nx number of rows. And how many number of columns? The same as n dot of ny, because y and e have the same dimension. Now let's see the b vector also. The b vector has a x0 and all of the remaining as zeros. A into x0 will have an x number of rows and the remaining are zeros. Thus b1 is first we have a of x0 and it has an x number of rows. This part only has an x number of rows. And the remaining is zeros, which is n-1 of it. But since we can have multiple states, we multiply it with nx. This many number of rows, but only one column. Now we have totally used the first equality constraint. Now it's turn for us to use the second equality constraint, which is this equation. Let's take this into account so that we get these matrices and this vector. Here also, we should satisfy this second inequality constraint for the whole prediction horizon, starting from k equals to 1 to k equals to n. Now, one more time, let me tell you that for a system which has more than one outputs, for each time step, obviously, we'll have more than one outputs. So, this 0 will be more than 1. For example, if we have a system where there are ny number of outputs, then this will have ny number of outputs for each time state. Now all of these equations which are obtained from the second equality constraints can be arranged in a matrix form as shown below. Here I will be filling up the matrix. Now this has to be multiplied obviously with all of the unknown variables, and as we know, the unknown variables are u0, u1 all the way up to u of n, 1, because we have to take into consideration the whole prediction horizon. The second element is the x, then the error signal. Now to fill up this matrix, we have to look into this equation. Let us start from the first equation. In the first equation, let's say what is the coefficient for the term u0. Here there is no u0 at all. That means it is 0. For u1, it's also 0 because there is no u1. Now let's move forward to the second element, which are the states. The coefficient for x1 is minus c here. This is the first equation. How about x2? In this equation, there is no x2, so the coefficient should be 0. There is no x3 here. That's why it's again 0, and all the way it's 0 up to x of n. For e1, e2, all the way to e of n, there is no e term here, so all of them will take 0. Similarly for the y term, from y1 to y of n throughout the prediction horizon, in the first equation, there is y and there is for y of 1. Now let's see, for y of 1, if you see the first equation, the coefficient is 1, but since it can have multiple outputs, let us write it as I. Now, let's move forward with y2. As we know that in the first equation, there is no y2, so it is 0. For y3, there is no y3, it's 0, and also there is no y of n in the first equation. So it is also 0. On the right-hand side of the equals to sign, we have 0, but how many of them? And y number of them? Fine. So now we have finished for the first equation. Let's move on to time step number 2. Let's start again from the top. Coefficient for u0, there is no u at all. So all of them will be 0. u1 0, u of n minus 1 0. If you check the coefficient for x1, we see 0. You can see that there is no x1, so it should be 0. How about x2? We have a coefficient for x2, and that is minus of c. x3 to xn not present in this equation, so all of them will take 0. Moving forward to the error terms, there is no error term here. So e1, e2 up to e of n is all 0. Now, let's go to y1. Is there a y1 term in the second equation that we are looking at here? Nope. There is no y1. So it is 0. How about y2? There is a y2 term here, and it is I. There is no y3 in this equation, no y4, and also no yn. So all of them remaining are 0. To the right-hand side, we have this one. So we have finished the second also. Similarly, in the same way. We can fill up all of the remaining equations for the whole prediction horizon. If we do that, we will get the following matrix. This is from the second equality constraint. So we write 2 here. But this one is for the control inputs. So it is u. This one is also from second equality constraint. But it is for the control inputs. This one is for the states. So we write x here and so on for the remaining 2 parts. Now if you see that AE to u are all zeros. So we can write AE to u is all zeros. But how many number of rows? Since this is associated with the measurement equation, which is here. So it should have n dot of ny number of rows, because of the measurement equation. But how many number of columns for this one? We have to see that this is being multiplied with the control inputs. That's why the number of columns is n times of n for the control inputs. Now let's go on to the next matrix. The next matrix is very similar to what we also obtained for the previous first equality constraint. And here it is that it has minus C on the diagnose. This matrix has a special structure, which we can write using Kronecker product as follows. Now, let's move on to this matrix, which is AE2E. AE2E is all zeros. So it's very easy to write. How many number of rows? It is associated with the measurement equation. So we can write AE2E. So this many number of rows. How many number of columns? This gets multiplied with the error signals. So an error is associated with number of outputs. That's why n dot of ny number of columns. AE2y is an identity matrix, as you can see, because we have I on the diagnose. In MATLAB, this we can write it as identity matrix of n dot of ny. And also if we see the BE2 vector, we can see that it has all zeros. Ny number of zeros, ny number of zeros, ny number of zeros, all the way n number of times. So n dot of ny number of total zeros is inside this vector. Now we have calculated the necessary matrix X using the second equality constraints. So this is also finished. Now we have the last constraint left, which is the error equation. And using this last constraint, we will make the matrices for the last row, N4BE3. Let's do that. Since this constraint has to be satisfied for the whole prediction horizon, let us do. So from k equals to 1 to k equals to n. We are taking the reference to the right-hand side because the reference is known throughout the prediction horizon. Now we have to arrange all of these equations into matrix compact form. Let me start writing the matrix from here. And also let me write my unknown vectors. As you already know, they are the control inputs, the states, the error signal, and finally the outputs. This is our z vector. We'll write all of the known quantities here. Now let us first look at this equation, which is the first equation. Since in all of these equations there is no u term and x term, that means all of the coefficients multiplying to the u's and also to the x will become 0, no u not. So we have 0, no u1 again 0, and all the way through u of n-1 that was. For the u similarly for x there are no x in this equation, so all are zeros x1 by 2x of n. Now, let's go on to the error part, and that is what we have it here. As you can see in the first equation, we have coefficient for e1, which is here, and that is 1. Since it is a MIMO system, we write this as I. There is no e2 term here, so e2 will be 0, e3 also 0, all the way to e of n will be 0. Now the last part, which is for the y's, look at the first equation, and here we have y1, and the coefficient for y1 is I. There is no y2 here, y2 is 0, there is no y3 here, 0, and all the way up to y of n. Now, let's look on to the second equation, this one. As also discussed in this second equation, there are no u's and there are no x, so all of them are zeros. When we go to the error part, we can see that there is no e1, so e1 is 0, however there is e2, and then we have I for e2, there is no e3 here in this second equation, no e3. And similarly, there is no e of n. For the y part, from the second equation there is no y1, 0, there is y2, which is I. No y3 and no y of n. Similarly, we go on filling for the remaining equations for this error equation. Let's look for the last one. For the last one, no u terms, no x terms, all zeros. And here there is only e of n, so it will be 0. e1, 0, e2, however, n is I. And also for y there is only y of n, no y1, no y2, but there is y of n. Thus we have finished the left-hand part of all of these equations. Now let's go on filling the right part. From the first equations, the right part, which is r of 1, is known, so here we have r of 1. From the second, this is also known. We have r2 and so on. We have all the way up to r of m, and these are the references which are known, thus this gives rise to the vector BE. But from the third equation, which is the error equation, this part is for the part of the A matrix, which is AE, but from the third equation, and then it is associated with the control input. Similarly, this is for the error, and this one for the outputs. Now, as we can see, the AEU and AE3X are 0 matrices, which are easier to write, but how many number of rows should be there? Since this is associated with the error equation which is here, it will have n dot of ny number of rows ny, because we may have multiple outputs and thus multiple error signals, and n, because we are taking into account the whole prediction horizon. And how many number of columns will this matrix have? This matrix will be multiplied with the use, thus it will have n dot of nu number of columns. In the same way we can write 48e3x. This denotes the number of rows, this denotes the number of columns. Here AE3E is an identity matrix where the diagonal elements are all ones. Using the Kronecker product, this can be written as follows, or simply it can also be written as identity matrix. But how many number of rows and how many number of columns? N dot of ny number of rows and n dot of ny number of columns, and similarly the A3 matrix is also an identity matrix. This one in MATLAB we can write it as follows. And the B matrix is a vector containing the reference values for the whole prediction horizon length. And this has a size which has n dot of ny number of rows, and since it's a vector it has only one column. Thus finally we have all the elements that is needed to make the A matrix and the B matrix during the standard formulation of the equality constraint as shown here. Now we can write AE and B matrix, and this AE and B matrix has all of these elements which are found. The question remains, how about this inequality matrix or inequality constraints in the standard QP formulation? In our original LQ problem, which is a control problem, there is no inequality constraint, we simply have a quality constraint. Thus, when the original control problem does not have inequality constraints, then this AI matrix will be simply an empty matrix. And this BI vector will be simply an empty vector. Thus, for this particular example, as we don't have inequality constraint, AI and BI are simply empty matrices in vector. But if the original problem had some inequality constraint, then we cannot write like this. If the original problem has inequality constraints, then they should be changed to the standard formulation by making structural matrices and structured vectors, just like we did for the equality constraint. Similarly, the question remains, how do we handle the bounds? The bounds on the unknown vector z. If we see the original problem one more time, if you go up, which is this one, nothing has been stated about the bounds. There could have some statements about the bounds, but for this particular problem there is nothing written there. So if nothing has been stated into the bounds, then we can simply assume that the unknown vectors can take any values from -infinity to +infinity. Thus, for this particular problem, we handle the bounds as follows. The lower bound for the unknown vectors, z, can be -infinity. All the elements of z, which are nz number of them, should be -infinity. Thus we are using these ones. -infinity multiplied by 1 nz number of them will give us nz number of -infinity. Similarly for the upper bound. If you remember that one of the variable that is in vector z is the control inputs. And in most of the cases the control inputs have some bounds. So in such a case where there are bounds in the control inputs, how do we deal it then? So if you assume that our control inputs are against the normal values, then we cannot handle them. Assume that our control inputs have a lower bound u of L and upper bound of u of u. How do we include this information into the unknown vector z? Recall that unknown vector z has elements u, x, e, and y. All of them have been made either -infinity or +infinity for the lower and upper bounds. Now we have to modify for u, and the modification can be simply done as follows. As you can see, we have introduced ul, or the lower bound on the control input, by taking the Kronecker of the lower bound vector with 1. If you take the Kronecker product, then we will have n dot of nu number of u of L, included in this lower bound vector. The remaining variables should still have -infinity, or the remaining lower bound should still have -infinity. Thus, total number of lower bounds minus for the control inputs only should be made -infinity as follows. Using the same style, we can also write for the upper bound z of u. This is the way we modify the lower bound for z vector and the upper bound for the z vector. If you want to include the bounds on the control inputs, Here inside the bracket it means this many number of rows and one column. The same thing applies here also. I will explain here why we need to extract the optimal solutions from the z-vector properly when we are plotting the controlling inputs, the states, and the outputs, and also the reference values. Now if you remember that the vector of unknowns, which is the z-vector, contains the following elements. When the QPOASES solver is used to solve the optimal control problem, it will also return the optimal solutions for these unknown variables in Z in the same structure. This means that Z-optimal, which I will write with Z star. Star represents the optimal values or the best values returned by the QPOASES solver, will have the same structure. Now, as you can see from this optimal vector of unknowns, it contains all of these terms together in a single vector. Now, if you want to plot states, then we should take out states properly from this vector. If you want to plot the outputs, then we should take out the output vector or a part of this Z only for the outputs in a proper way. For SISO system, this becomes straightforward. However, for a MIMO system which has multiple inputs and multiple outputs, little care should be taken. For example, in a MIMO system, we will have multiple states, multiple inputs, or multiple outputs for each time step. So for each time step, if this axis is for, let's say, U, then for each time step, it will have multiple values of U. A total number of control inputs that is available in the process will be here, will also be here, and so on throughout the horizon. For example, if we said that the process had 2 control inputs. So let's say this is the process, and this process has 2 control inputs. Let's say control input number 1 and control input number 2. For each time step, from k equals to 0 to k equals to n-1 for control inputs, we will have the optimal solution for both control inputs. That means for both U1 and U2. This represents the optimal solution. And if you look at the first one, which is this one, this is the optimal solution of the control input for time step k equals to 0. So here at the initial time step. So at k equals to 0, this U0 star will contain the optimal values for both the control inputs, which are U1 and U2. So U star will have U for 1. As for control input number 2, it is also valid for other time steps throughout the horizon. That means for time step k equals to 1, the optimal values, which is U1 star. This should also contain the optimal values for both control inputs. So this one will also contain U1 and U2. So if you look at this example for the control inputs, let's try to split up this one and see how it looks like. This will look something like this one. Each U1 for this example will have 2 control inputs. For time step 0, optimal solution, but for the first control input. Time step 0, optimal solution, but for the second control input. And this much was for k equals to 0, for k equals to 1. Or for the next time step, which is here, we will also have 2 control inputs. So U1 for k equals to 1. Optimal values for the first control input. U1 for time step 1. Optimal values, but for the second control input. And so on. The structure follows all the way through U of n-1 time step. Because the prediction horizon for control inputs starts from k equals to 0 and ends at k equals to n-1. So the last step, optimal values for the first control input. For the second control input. This will be the structure for a MIMO system. Now if you want to plot the first control inputs, let's say you want to plot U of 1. One of the control inputs in the process against time or discrete time k. At k equals to 0 you need to plot. Let's say this is U star 1. But for the next time step k equals to 1 you need to plot not the second element of the z-vector, but the third element. Because the second element is for the second control input. But you want to plot the first control input. So we have to plot this one. this one. If there was for k equals to 2, u2 star of 1, and so on, up to here. So for k equals to 1, let's say it is here. For k equals to 2, let's say it is here. And so on, all the way to k equals to n. And so on, all the way to n minus 1. Let's say this is somewhere here. And that will be for the first control input, which means that the signal to be plotted for the first control input is not in a ready-made form. And you cannot simply plot the first n minus 1. You should pick out properly. The same thing also is valid for the states and all of the other remaining elements of the z-vector, or in other words, the elements that you are interested to plot. For example, if you want to plot the outputs, let's say it has 2 outputs, then make sure that you pick up the right signals or data from the z-vector. If you are interested, for example, to plot y of 1, in MATLAB there is an easy way of doing it, and that is by using the command reshape. Now let's assume that the optimal vector for z is denoted by z_opt, which means optimal values of z. And this is equivalent to z star that we have written here. And please remember one more time that z star contains all of the u's. If MIMO u's or multiple inputs, then all of them here. All the states here. If there are more than one state, everything is here. The error and the outputs. So before we can plot our signals, which usually are the input signals and the output signals together with the reference signal, then it's a wise idea to first extract all of the u's, then extract all of the x, then e's and y's separately. Let us first do that. In MATLAB, we can use the following way to extract the u's, x's, e's, and y's. So here z_opt is the z star vector. Let's first extract the control inputs. The control inputs come first. So it starts from the first element. And how many control inputs we have? We have n dot of n number of control inputs. So for the control inputs from the z-vector, let's look at here. U star, x star, e star, and y stars. This u's, of course. It will start from the first row. It will end in n dot of n number of row, because we have n dot of n number of control inputs in this vector. That's what we have done. It starts from 1, and it ends to n dot of nu row. For the states, it starts from n dot of nu plus 1, the next element, and it ends obviously here. And that vector contains, or let's write it this side, n dot of nu plus n dot of nx. So this is the row position for the x vector, or the end of x part. Let's say n dot of nx. N dot of nu already comes from the top one, and it has n dot of nx number of elements just for the x. So we plus it. The part for the errors, of course, starts from n dot of nu plus n dot of nx plus 1, the next element, the next row. And it goes all the way to this part plus this many number of rows plus this many number of rows, which is n dot of nu plus n dot of nx plus n dot of ny here. And similarly, we also extract the last element, which is the y, or the outputs. So here we are simply using the colon operator of MATLAB. So it's just to see the total number of rows that are in U vector, the total number of rows for the x vector, and so on for the en, and so on for the y vector. So indexing is very important. Correct indexing should be used. Now this UA is again a vector, but it contains only the control inputs. But still, this UA, which is this one here, still contains both the control inputs, or let's say all of the control inputs that is available in the process. For example, this UA will contain, if there are 2 inputs, U01, U02, 4k equals to 0, U11, U1, and for second control input, 4k equals to 1, and so on. Now let's extract only for the first control inputs, because we want to plot the first control input, acting on the process. For this, let's use the reshape function in MATLAB, as follows. call the reshape function. And inside this reshape function, pass in this UA or the component of the z vector, where there are only control inputs. Nu is the number of control inputs, and of course n is the prediction horizon. If you do this one, out from here, the outputs, which is in utemp. This utemp will be arranged as a column as a data, and the rows as signals, which means that each row represents one control input. So if there are two control inputs in the process, there will be two rows, or nu number of rows, let's say, and columns as the data. So from this vector, it will rearrange the vector so that it will have nu number of rows corresponding to each control input, and n number of data corresponding to the whole prediction horizon. Okay. However, in Simulink, we will plot the necessary signals like u's or y, and also the states, using array plot. And there is a small thing to understand when using array plot in Simulink. And it's also written here. The array plot in Simulink accepts signals in a format such that the column represents the different signals, and the rows represents the data for each signal, which is just the opposite of what the reshape function gives us. That's why we need to transpose it. So when we transpose this utemp, finally, we will get the signal that we want to plot, which is u. Now we can plot this signal using array plot in Simulink. Now this u will contain two columns and mainly rows. The first column will be the first control input. So this u will have this format. Many elements in the first column, and in the second column, also many rows. So this is for the first control input u1. And this column is for the second control input u2. Each row represents the data for each time step. For example, if I want to just get the first column, then of course, which is the control input number 1. So u1 would simply be u of all of the rows, but only the first column. And the second control input would be all the data for the whole prediction horizon, but the second column, and so on. If there are more than two control inputs, this was just an example, taking into account just a control input. But it is also valid for all of the elements that are present in the z-vector. And we know that in the z-vector we have the states, we have the error, and we have the outputs. So, we should also, for example, use the reshape function for, let us say, for the output vector. Use the reshape function. Instead of u a, you have y of a. Instead of n, you have, of course, n of y. And this will remain the same. And out from there, you will get y temp. And you have to transpose it. At its heart, MPC is a profound idea. We guide systems into the future not by reacting to the present, but by optimizing over possible futures and committing only to the first step. It's a formalization of prudence. The mathematics we've laid out, the cost, the constraints, the receding horizon, provides the rigor needed to trust this idea with safety-critical systems, cars, planes, reactors. If this blend of mathematics, computation, and practical philosophy resonates with you, you're in the right place. Subscribe to explore more ideas that shape autonomous systems. A question to ponder: in what domain do you think the predictive aspect of MPC provides the most dramatic leap over reactive control? Share your thoughts below. Thank you for engaging with the depth of this topic. Keep thinking ahead.